Hello Math 8 students, this is Utah Middle School Math Project 9.2b, Properties of Dilations. To get started, we have the situation where Miss Williams gave her students this grid and this triangle that's shaded ABC. Then she asked her students to create a triangle that was the same shape as the original triangle, but has side lengths that are 3 times larger. Micah created triangle LMN, and Nadia created triangle ADE, and you can see those here on this grid. So then the teacher asked the class, who did it correctly? Nadia or Micah? And Aya says they were both correct. Hendricks disagrees and said they couldn't both be correct because the triangles were not in the same location on the coordinate plane. Students in class have already had a chance to discuss this, so now we're going to turn it into a class discussion. Who do you agree with and why? Thank you for these hands. Emery, get us started, please. Aya? Why Aya? Okay, the same one, just translated, so it still is going to be the same. They still met the goal. What else do you have to say, Jaden? One's translated and the other one's dilated. Okay, different transformations. Good. And last comment, Gracie. Great job. Did you read ahead in the lesson? No? You just know. Okay, good job. I like all of those thoughts, and you're all correct. One can be viewed as they are both correct. They made triangles that were both 3 times the size. They're just in different positions, which means maybe they used a different sequence of transformations, as Jaden mentioned. Maybe they translated it, and then the other one they dilated. And Gracie knows a little bit more about dilations, and she says they just use different centers of dilation, which is what we see on the next page. So I hope at least at this point you guys are agreeing that yes, these are both triangles that are 3 times the size. And my tablet still is not working. I thought that things were going to be nice and it's not. All right, giving up on the slate, it's not working. So we are going to just type the response that we agree with Aya. The triangles, both triangles are 3 times as big. Before we discuss much further, how do you know that each triangle is 3 times as big? What did you do to kind of compare and make sure that it actually met those qualifications? What did you do, Daxton? Okay. Okay. So AC is 3. And the corresponding segment is AE, and we can see that that's 9. So 3 times 3 is 9. That's 3 times as big. And we can see that LN is also 9. So yes, we can see that that is the case. I hope you confirmed with multiple ones though too, right? So we also should have compared BC. BC has a length of 4. And the corresponding segment is DE, and that has a length of, I didn't count it, but I'm assuming that it's 12. Did you guys count it for me? All right. And same thing with MN, right? So they, just going with lengths, it works out perfectly. Just a side note, if I were teaching things in order, this is all the way in Unit 9 in Utah Middle School Math Project. So you may have had, or we skipped lessons on how we can measure the length of this side. So we're not going to worry about the length of this diagonal. We skipped those lessons. We'll be getting to those soon. But for right now, just measuring these other 2 is enough. So we do know, and just measuring those lengths kind of confirms that that is 3 times as big. So let's discuss about that whole dilation thing. As it says here in the previous example, Micah and Nadia both dilated triangle ABC. Even though it didn't appear that way, Jaden thought it's not a dilation, it's just a translation. It is a dilation. A dilation is a transformation that produces an image that is the same shape as the original figure, but the image is a different size. In other words, it produces a scaled copy. So is it a scaled copy? Yeah. Are they in different places? Also true, but they are both scaled copies. So a dilation did occur. What we need to remember is, you might remember, yep, it's just not working. You might remember this screen where we had different things that we revealed, different properties that we revealed, and we're going to go over that in a second. But one of those things that we revealed is every dilation has a center of dilation and a scale factor. The center of dilation is a fixed point in the plane from which all the points are expanded or contracted. So today we are going to be learning a little bit more about how we can find that center of dilation, or how that center of dilation affects these different scaled copies or dilations. Let's keep reading though. The scale factor describes the size change from the original figure to the image. We use the letter R to represent the scale factor. So later on, I might say something, oh, it's not working. I might say something like R is equal to 3. That just means that the scale factor of the dilation is 3. We just use the variable R most of the time. And if that letter R, if that variable R is greater than 1, then it's going to be an enlargement. If it is between 0 and 1, then it is going to be a reduction. So the next point that we want to, or these next blank spots, we need to find the center of dilation for each of these. It is possible. Any ideas how we are going to find the center of dilation? I want you to think back and review kind of some of the things that we saw in our last lesson. How can we apply it here? And I feel like Gracie knows. Gracie said that they have different centers of dilation, right, Gracie? Do you know how to find those? You can, no? Okay. Any thoughts on how we can find that center of dilation? Discuss. Start bouncing some ideas around with your group. See if you can figure that out. Here's a hint. You're going to need a ruler. We're going to pause the recording. Okay, what ideas do you have? How can we find the center of dilation? We'll start with Sam. How do you know that? Okay, so you're remembering what we talked about last time, that the things should be lining up, right? For example, if I were to draw a line, or for you guys, start with just holding your ruler up. Hold your ruler up so that it lines up with D and B. Because remember, D and B are corresponding points, right? So line those up, and then we're just going to extend that line. And repeat that. C and E are also corresponding points. So you can line your ruler up and extend that line all the way. Where are those lines intersecting? At A. And that confirms, oh, it's just not working. That confirms that A is going to be the center of dilation for Nadia's triangle. That is not what I wanted. I wanted this one here. Okay, that's the center of dilation there. Now, Sam gave you a good hint. Apply that. How can we figure out the center of dilation for Micah? Where is Micah's center of dilation? Again, let's review. D and B were corresponding points, so I took my ruler, lined it up, drew that line, extended it, did the same thing with E and C that were corresponding points, lined it up, and I said, hey, wait a second, those intersect right there. Repeat that process. See if you can find Micah's center of dilation with your groups. Ready, set, go. Let's pause the recording. Okay, how am I going to find the other center? What process should I go through? Tage? Okay, good guess. However, here's the part that you're not taking into consideration. M and L, those are all parts of the same triangle. So lining those up doesn't mean anything. That just means that we're forming a triangle. The part that is probably lost in doing this one first is we can see that D and A are part of the same triangle, just like B and A are, but what I was really doing is lining up D with B. Those are two separate triangles. Do you see that, Tage? So let's make some adjustments. What should I do? Maverick? Okay. That's, yes, let's pause there. Don't just go straight to it's the origin. You're right, but how do we get there? What we're really doing is we're saying M and B are corresponding parts, right? So we're going to draw that line that goes, or line up our ruler from M through B and extending it back so that we can see what might be happening. Okay, continue on with that. Someone else pick up. We lined up M and B. Those are corresponding parts. So I lined those up, drew that line. What else would I do, Fitz? Say that again. We're not done yet. all we've done, so maybe let me change the color here so that you guys can see what's happening. I'll even change it. We're going to go purple. So these green lines, focus on D and focus on B. Those are corresponding parts. So I drew a line, or I lined up my ruler to go through the corresponding parts. I drew that line so that when I move my ruler, it's still there. And then I repeated that. E and C are corresponding parts. So I line up my ruler so that E and C are in the same line. Draw that line so when I move my ruler, I can still see it. And when I did that, I saw that this green line that connected D and B and this green line that connected E and C intersected right here. But now I'm repeating that process looking at a different set of triangles. I'm looking at mica and I'm looking at the original. Mica's corresponding part is M. So I'm taking M, seeing that it corresponds with B, so I'm lining my ruler up to those points. And again, I'm extending that line so that when I move my ruler, or I'm drawing that line so when I move the ruler, I can still see that line. I don't have intersecting anything right now because this is just one purple line that connects M and B. There are other points that I need to connect. For example, N. What is the part that corresponds with N in the original triangle? Siley? C. So I'm not done. I need to continue to connect all of those corresponding parts. So let me try that again. N and C correspond. So I'm going to line up my ruler so that N and C, I need to make those adjustments, N and C should be lined up on that ruler. And again, I'm just extending that line forwards, extending the line backwards so that I can see where it's possibly going to be intersecting. Ignore the green ones. The green ones were for a different triangle. Just focus on those purple ones. Do you see what's happening with those purple ones now? Fitz, does that make sense? You were focused on the purple with that green before I had color coded, and so you were looking for an intersection point that wasn't really relevant. But now if I color code, I can see this purple line and this purple line intersect. Let's go another step further. Take a look at L. There is a corresponding part. For L in the original triangle, it's all covered up now, but that would be corresponding part, or point A. Repeat that process then. What is that going to look like? I need to connect L to A and extend that, and there hopefully is further confirmation. Where do all three of those purple lines, all three of them intersect? At the origin 0, 0. So yes, your assumption that it was the origin is correct, but this is how we find that center of dilation. We connect those corresponding points. And when we see all of those corresponding points all stemming from this point right here, that makes that the center of dilation. So for mica, that center of dilation was that point 0, 0. Let's write that down. And again, I'm going to have to be typing since my stuff is not working. Nadia's center of dilation was point A, which was the coordinates 2, 1. And Micah's center of dilation was the origin, which has the coordinates 0, 0. So we're going to be practicing more with dilations. We're going to be creating some dilations. We're going to be looking for information about dilations that have already been done. Let's quickly review some stuff from our last lesson. Tell me some things that you know about dilations and I'll reveal what is underneath. You reviewed this before we started the recording, so there should be lots of hands right now. Tell me something you know about dilations. Thank you. Gabe, get us started. Preserve angles. You guys are just going to make this easy and go in order, aren't you? You preserve angles. The angles stay the same, just like in scaled copies. What else do you know? Let's go, Hayden. Say that one more time. Yeah, side lengths are going to be scaled up or down according to our scale factor. Jamie. They produce non-congruent figures. Because if they're changing size, then they're not going to be congruent. Charlie. Requires a center of dilation and requires a scale factor. So all of those things are going to be necessary for what we're going to be practicing now. Oh, let's list some more properties. These are some great properties that we just saw. Let's list some more properties. We're going to use that example on the previous page, which I have here so that we can still see it. We want to complete each of these sentences. Under a dilation, corresponding angles are, you tell me, corresponding angles are what? If angles are preserved, is the angle measure going to change? No. So corresponding angles are congruent. Let's use the fancy math word. They're congruent. That's even fancier than the same. They are going to be congruent. This is a new one. This one is maybe not quite as obvious, but it's still worth mentioning. Under dilation, corresponding segments are, so focus right here on segment DE and segment, oh, not that one, I'm sorry, DE and BC. What do you notice about those? They're parallel, exactly. So that one maybe is not something that is going to be super duper duper helpful, but it might be something that we can use to check our answers later. Corresponding segments are going to be parallel. Under a dilation, corresponding vertices are, I'm going to give you another fancy word here, collinear, on the same line. That's how we find that center of dilation. Because B and D were corresponding, so they're on the same line. M and B are on the same line, and that line is going to go all the way back to that center of dilation. So under dilation, segments connecting corresponding vertices, where do they all intersect? At the center of dilation. So if we need to find the center of dilation, we're going to connect those collinear points, all those corresponding points. Find where they all intersect, and that is our center of dilation. Anyone need more time to write those down? All right, let's move on to some practice then. It says find the dilation of ABCD with center P and scale factor 2. So here is, I forget, I cannot use my tablet. This is going to be very challenging. Here's P. That's going to be the center. And the scale factor is 2. So what I'm going to do to get started, I'm going to draw lines that go from P through each one of those vertices. Because I know that A prime is going to be somewhere on this line. And D prime is going to be somewhere on this line. And B prime is going to be somewhere on the line that goes from the center of dilation through B. So as I'm setting up my ruler and drawing these lines, make sure that you extend it all the way to the edges of the grid. And if I'm looking for something, I want to find A prime. I know it's going to be on this line somewhere, but I need to make sure I'm using that scale factor of 2. Here's what I need to be paying attention to. How far away is A from P? Again, it's hard to measure the length of those diagonals, but I can see that it's up 2 and back 1. So if I multiply that by 2, that is now going to be going up. 2 times 2 is 4. And it went back 1. Well, 1 times 2 is 2, so now it's going to go back 2. And did I land on that line? Yeah, exactly, just like I said I would, right? It's going to be somewhere there, and that is going to be my A prime. Let's repeat that process. Let's go on to the next one. I know that B prime is going to be somewhere along this line, but I want to make sure it's precise. So I need to figure out how far away is B from P so I can make sure that B prime is twice that distance. So same type of thing. That would be 1, 2, 3, 4, 5 across and 2 up. Well, let's multiply that by 2 then. That's going to be 5 times 2 is 10. So that's 5, 6, 7, 8, 9, 10. And it was just 2 up, 2 times 2 is 4, so now it's going to be up 4. Have we found B prime now? Yep. And just like we said it would, it landed right there on that line. There's the B prime. Repeat that process. You guys can probably do it faster than me since I don't have my tablet. Things aren't working for me. You guys can probably do it a little bit faster. C is also 5 down, or excuse me, 5 across and 2 down. Doubling that, I'm going to do this a little bit different way. I went to the right 5 and down 2. What if I just did that a second time? Isn't that the same as doubling it? Yeah. So there is my C prime. And last one, D. D prime is going to be somewhere on this line, and D is down 2 and to the left 1. So if I repeat that and go down 2 and to the left 1 again, I'm going to find D prime right there on that line. Now we found all the points, but we technically are not done. We still need to create that quadrilateral, so I'm just going to connect those, go from A, oops, wrong line segment tool though. A prime to B prime, B prime to C prime, then to D prime, and then close up that figure back to A prime. There's my new quadrilateral. It was a lot of steps. Yep. But are they hard steps? No. Time consuming, maybe. Hard, not so much. A fun game of connect the dots. I like your attitude. Okay, now let's try it with the triangle. Using this grid, we're going to find the dilation of triangle QRS with center T and scale factor of 2. Good news, they've already drawn those lines for us, right? So that's helpful. Now we need to make sure that we are finding the correct points, knowing that Q prime is going to be somewhere here. R prime is going to be somewhere here. S prime somewhere here. Where exactly? This is where we just got to make sure that we're paying attention to the scale factor of 2. 2 first and then later 1/2. 2 first. So, same type of thing. How far away is Q from T? 3 and 1. So, let's do that again a second time. 3 and 1, and here is our Q prime. Yes, Emery. Nope, look at problem 2. Scale factor is 2. 2 first, and then is a scale factor of 1/2. Don't skip this one. I'm going to repeat that same process for R. How far away is R from T? 4 and 1. And again, I'm going to do it a different way this time. 4 doubled, so 4 times a scale factor of 2 is 8. 4, 5, 6, 7, 8. And 1 down, 1 doubled is 2 down, so there is my R prime. And last time with S, how far away is S from T? I measure that by going down 2 and to the right 2. So now it's going to be going down 4 and to the right 4, and that is my S prime. Draw that in place, Q prime to S prime to R prime, and R prime to Q prime. There is my new dilated triangle that is twice the size of the others. Things that are worth pointing out, some characteristics and properties that we just saw in our last example, or that we just wrote down. Notice, let me pick a line that I can use here. Notice QS is parallel to Q prime, S prime, right? Parallel lines there. We would see that with all of them. QR and Q prime, R prime are parallel. So we are seeing that those are parallel if we have done it correctly. Now you can do number 3. Now you can do 3 where the scale factor is 1/2. Center of dilation is still T, but now the scale factor is 1/2. Work on that with your groups. You can ask questions, yes. Mm-hmm. No, that's what your group is for. Instead of doubling all the links, we're going to half all of the links. All right, I have completed that dilation with scale factor of 1/2, so you can always check the screen. I'm going to pause the recording. Okay, let's take a look at the next type of problem. In the next type of problem, the figures are already dilated. So now we need to piece together the information that it's asking for. Okay, so in these figures, one figure has been dilated to obtain a new figure. That work has already been done, but it's our job to determine the scale factor and the center of dilation. Okay, for some of them, it has a coordinate rule. We'll address that when it's time. Do you see these two figures? Which one is the original? Since this is A, B, C, and this is A prime, B prime, C prime, the smaller one is the original one. So what is the scale factor then? Again, let's take a look at these distances. Oh, wrong pen. The distance here is 3, and the corresponding distance in the bigger one is 6. How does that 3 change to a 6? 2. So the scale factor is 2. What is the center of dilation? This one I hope is pretty easy to see. Yeah, it is 0, 0, or the point A. Here's what I want you to be checking as you're looking for this. Again, let me switch my tools here. I'm going to line up B and B prime, and I can see that that line goes here. I'm going to line up C and C prime, and that line goes all the way back to here. And A prime are already lined up, right? And A prime are lined up at A, the origin. So what is that center of dilation? 0, 0, or point A. We'll probably come back to that coordinate rule another time. I don't know if I'm going to address it. We'll come back to it another time, but not right now. Let's try the next one, and then I'm going to have you guys work on your own. Number 5. In the picture below, triangle ABC has been dilated to obtain triangle A prime, B prime, C prime. Is it getting smaller or bigger? Okay, and this time we're having a little bit of a harder time with the lengths because all of these are diagonals, so it's going to be harder to measure those lengths. But what I can always measure is the distance from what appears to be the center. Let's find that center first. Let's not just guess. Let's find that center first. What we're going to do, yep, I'm ready to go. We are going to line up A with A prime. Notice I don't know where that center is, so I'm just drawing the line, extending it probably way more than is necessary. I'm going to do the same thing. C and C prime, line it up. Set that ruler in place, line it up. I'm starting to see some lines intersecting, right? Line up B and B prime. Where do all 3 of those lines intersect? That is your center of dilation. So, center of dilation is, just like before, 0, 0. Now that we know that the center of dilation is 0, 0, since measuring these distances might be challenging, we can always measure the distance from the center. So let's focus on A and A prime. I can't use my pen tool. My tablet's not working. I keep on forgetting. How far is it to go from A to A prime? What's that distance there? No, I'm sorry. Wrong question. Wrong question. Don't answer that one. A to the center. 1, 2, 3, 4, 5, 6, 7, 8, 9? 9. And what is that distance from the center to A prime? 3. So how does the distance of 9 change to a distance of 3? What is that scale factor? Danielle? 1/3. The scale factor is 1/3. Okay, I'm going to leave the rest of them to practice for you. We'll go over as many as we can in the recording, but I want you guys to practice on your own. We're going to pause the recording now. Okay, give the other ones a try. Practice them first, and then after you've practiced them, then you can continue in the recording and watch how we do it. The first thing that I'm going to do is I want to try and find that center of dilation. So I'm going to connect these corresponding points with a line, L to L prime, and I'm just going to extend it back far enough that I can maybe see where it might be intersecting. And same thing, M to M prime, extending that back far enough that maybe I can see where it's intersecting. N to N prime, extending that far enough back. Hopefully you can start seeing an intersection. O to O prime, connecting that with a line but extending it back. And how about that? Looks like they are all intersecting in one spot. Makes that nice and easy. We just, ooh, that's a big let's see if we can make that smaller. They all meet right there, and I would call that point -6,3. -6,3 is that center of dilation. And now I'm ready for the scale factor. So with that scale factor, I'm going to be comparing these corresponding parts. So this has a length of 6, and the corresponding part in the new figure has a length of 3. How is that 6 changing to a 3? That must mean that the scale factor is 1/2. 6 times 1/2 is 3. And we can check that in a few other spots too. We can see that this length is 4. 4 times 1/2 is 2. So that scale factor would be 1/2. And the last one, again, finding that center of dilation by connecting all of those corresponding parts. A to A prime. B and B prime. I'm already seeing an intersection. Let's confirm that it works for that third one. C and C prime, extending that, and sure enough, that is also still too big. All intersecting right here, so we would just need to list those coordinates, and those coordinates are 5, 1, 2, 3, 4, 5, 5, 5. Center of dilation is 5, 5. And again, we can find the scale factor by measuring a couple of different things. We can measure the corresponding parts. So BC is 3 and B prime C prime is 6. So the 3 changes to a 6 by multiplying it by 2, making that scale factor 2. The alternative, another way that we can do this, is we can measure from the center of dilation. From the center of dilation to point C, that's 4. And from the center of dilation to C prime is 4, 5, 6, 7, 8. So how does that 2 change, how does a 4 change to an 8? By multiplying by 2 with that scale factor of 2. That's it for this lesson. So your homework is the homework section where you have more. All you're doing is identifying the scale factor and the center of dilation. Once again, for right now, let's skip this coordinate rule. Anytime you see that coordinate rule, just skip it. We'll get to that later. You have, looks like 7 homework problems, so it shouldn't take you too long. That's it for today. Thanks for watching, and we'll see you next time.